So everything I said up till now. Distance is what we call a magnitude, meaning it is only a quantity. Displacement is what we call a vector, which means it has a quantity and, oh crap, I shouldn't have said magnitude there. Son of a, sorry everyone, it's scalar, because it only has a quantity, and then quantity is where I wanted to write magnitude. Sorry everybody, it's Monday morning. Quantity and a direction. Now, here's the problem. Is a graph a drawing of what is actually happening? No, it isn't. It represents data, yes? And on a graph, what are the only directions available to me? Left or right and up and down on the graph. What are the only values, directions available to me, mathematically speaking? Numbers go up and down. Where do numbers go? Positive and negative. So the only directions I have with data is positive or negative. In the real world, I have many directions, don't I? So, we have to discuss what in the real world translates into data for our graphs. Everybody understand? And this is arbitrary. We have chosen this. Positive values are things like the following. When you are moving away from a starting point, it is positive. If you are moving to the right, if you are moving up, if you are moving east, if you are moving north. Those are some of the directions that we have assigned to positive values. So obviously then, what are the negative values? Toward, left, down, west, south. Is everybody cool? Now, you need to see a demonstration of something. If you are going to graph the distance I am about to travel, distance, right now, what is the time? 0, because we're about to start my graph, yes? At 0 time, have I traveled anywhere yet? No. Now, I'm going to start traveling, okay? Don't worry about the time. Just know that time is passing. Everybody cool? All right, ready? What was my distance? 3 positive steps. Because I went away from my starting point. Also, for me, I could say it's positive because I went to my right. Agreed? But for you, you could say I took 3 negative steps because I went to your left. Do you understand? You could also say because I was going north, I went 3 positive steps. Everybody cool? The important thing here is my distance is 3 right now. Agreed? Because distance is scalar. It only has a quantity. So I've gone 3 steps, yes? Now, keep clocking my distance.
0.
What is my distance now? 6. Because I went 3 steps there, 3 steps back. Distance is scalar. It has no direction. It is like the odometer on your car. If I drive my car from my house to school and back home, I have driven 10 kilometers. But if you drive by my house in the morning and see my car there, and drive by my house after school and see my car there, do you know if my car has gone anywhere? No. But the odometer knows it's gone that 10K. Is everybody with me? So my distance right now is 6. What is my displacement? 0. 3 positives, 3 negatives. If you had your eyes closed, you wouldn't know I moved. Is everybody cool on the difference between distance and displacement? Yes? Yeah. All right. Good. That went well. And you were also to try and explain Alicia's race here. Alicia's race is different than what you think it is. So what happened? How many lines of text do I need to describe this at least? 3, because there's 3 stages of the graph, yes? So what is happening from 0 to A? She is accelerating. The race has started and she is running as fast as she can. So for the first 2 seconds, she is accelerating up to what speed? 8 meters per second. Hold up a sec. What Zach is saying is he wants to do 8 divided by 2. But that gets you a speed, which is distance over time. I have a speed. Understand? Got to be careful. Is everybody cool with that? All right. What is happening from A to B? She is staying at her top speed. Her speed isn't changing. She is not sitting still for a race because we are clocking her speed and her time, not her distance and her time. Does everybody understand? Okay. So she maintains, I know the screen just went out. It's been going out all day. It's been really bad today. If it continues to do so, I'll have to go to the projector, which is a bit of a pain, but I had to do it for the other class. And then what happens, what specifically happens at point B?
It stops down.
Why? What happens at point B? She finishes the race. She does not stop running because she cannot stop. What is happening from point B to C?
She's slowing down.
She slows down. Why isn't it straight to the ground? Because she didn't run into a wall. She ran through the finish line and started to slow down. Does everybody understand? Now, you can find out a bunch of stuff from this. Zach wanted to do something with the slope, right? What he can do with the slope here is get her acceleration. Her acceleration was 8 over 2. So she was accelerating at a rate of 4 meters per second squared. Because meters per second in seconds. Right? This is physics. And then here, there was no rate of change because her speed didn't change over time. So that's a 0 acceleration. And then here, it's negative 4 meters per second squared. That's physics. Physics 11. You don't need to worry about it. But suffice to say, that slope thing, that rate of change thing that I taught you guys about distance and time, you're going to use it again and 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 again. And again 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 and again. So you really need to know how to deal with it, okay? The slope of a graph will always give you information. And it's the basis of calculus. Okay? So is everybody cool with this? All right, what else did I ask you to do? That was it. Yep, okay, so let's go on to 154. And now that you know a little bit more, you guys try these. Do your drawings on the left-hand side of the page in case you draw them wrong. Just do 5 and 6 for now. And try to do them on the left side of the page just in case you make a mistake. Or do them in pencil. Are we ready to talk about 5 and 6 yet? No rush. I'm not trying to rush you. I have nothing but time. I also don't want to waste any. Or do people want to have a couple more seconds with it? Yeah, no problem. No problem at all. Let's talk about the first one. What's going to be the independent variable? Time. Excellent. Why? Time doesn't depend on anything. It goes no matter what, whether I'm swinging on a swing or not. So that means height is over here. At 0 time, what is the height of the swing? Wouldn't swing very much if its height was 0. It'd be sitting on the ground. So it has to be a little off the ground, doesn't it? First mistake most people make. They have the first dot at 0. Remember, it's not a drawing of real life. It's a drawing of data. The swing can't possibly be at 0 or it won't swing. Next, what happens? How do you swing on a swing? You have to stand up, don't you? And back up, right? If I just stand up on the swing, nothing's going to happen. The swing stays there. But if I back up, the swing lifts up a little with my ass, right? So, what happens to the height of the swing in the first second? It goes up how much? Very, very little, yes? And it's probably going to go up kind of slowly because I'm backing up, yeah? So it's going to go up very little with not a very steep line because it's slow. Then what happens? It goes downwards. To what level? The original dot. Does it go back down to 0? No, because that would hurt your butt when you hit the ground, wouldn't it? Faster or slower than this? Faster. Then what happens when you start pumping? I go a little bit higher every time. And a little bit faster every time. Everybody with me? Now, how many of you drew this? Somebody every year draws that. Well, you're swinging like this. You're swinging so fast, you're going back in time. You're swinging faster than the speed of light. None of you drew that, did you? Why? Because a graph isn't a drawing of what happens in real life. It is a representation of data. Now, everybody understands why the slope gets steeper, yes? Will the slope ever be vertical? No, time must keep passing, right? Everybody good? All right. Did everyone draw it right? Ish? Where were your mistakes? My guess is a lot of people started at 0 and brought the graph back down to 0. So that's easy to fix. And I'm betting that a few of you forgot to make it steeper and steeper as you go faster and faster. Because you're passing through the same distance or more distance in less time. Everybody cool? All right. Did you get to 6 or do you want a moment with it? Especially since you just learned something new. Would everyone like a moment with 6? Go ahead. What's different about 6 than 5?
Distance.
Hannah?
It's distance and it doesn't ever decrease.
Yes, since it's distance, not height, it can't ever decrease. So, what would it look like? Time would be down here. Distance would be over here. Now, we could just draw it, or we could actually draw it sensibly. How do you start a 400-meter race? At time 0, 0 distance. When the gun goes off, what do?
You run.
You run as fast as possible up to your comfortable pace, yes? So, is the first line going to be steep or shallow? Steep-ish, right? Because you want to get into a good position. Then what happens? You get down to your running pace, right? Probably less steep. So, and over time. Agreed? Now, a 400-meter race is probably going to be measured in seconds, yeah? Because the record is like 55 seconds. So we're going to slow it down, pass time, but pass less distance. What should I do at the very end of a race? No, before the race ends, shouldn't I have a finishing kick? So what will happen here? I'll get another steep bit up to a maximum of here. What's here? 400. And here is the time. Distance versus time for completing a 400-meter race. Well, once I hit 400, the race is over. So after that, I don't care what happens to my time. Does everybody understand? How many people? You don't need to vote. You don't need to show, but recognize if you did it right or wrong, right? And be happy. What are some mistakes you could make? You don't want anything going downwards because this is a scalar. He is traveling or she is traveling that 400 meters, right? So you don't ever want to go down. If it was displacement, where would the graph end up? Back down here, where we started, right? Okay. Which, surprise, surprise, is the very next question. So, this is tricky. Now, again, there's what's really happening, and then there's logic involved, right? Really what's happening is in black, this is kind of the easy way. It would look almost the same as the displacement time, wouldn't it? Right? You'd start off fast, going away, right? You'd slow down to a running pace, and then what would happen halfway through your time? You'd start going back, right? And then you'd have your strong finishing kick at the end. Everybody understand? In reality, is it that? A track's an oval, isn't it? So when I start here, I'm going away, 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 away. Now, here, I'm still going away, aren't I? But eventually, this is when I'm least away from my home, right? So if I was measuring actual distance, the graph would look weird, wouldn't it? Because my distance away is really only this. But I'm traveling this distance. Does everybody understand? Is everybody with me? Which one is enough for me that you get the concept? The black or the red? Black's enough. Everybody understand? If you really wanted to get technical, you would have to measure the distance from this starting point to every point of data you had. Like if you took a measurement of how far she had traveled every second, it would look weird. It would give you a funky graph. But eventually, it would come up to a peak and back down to home because we are talking about displacement. The concept is displacement comes home, distance carries on. Is everybody good? Yeah? Okay. So, now, position. Hey, you haven't used that word before, Mr. Myers. Which of the two, displacement or distance, do you think position attaches to? Displacement. Because once you have a position, you must have had a direction. Yes? Everybody understand? So, read this question carefully. It's position time as you travel to school. So since you're not going home, is this graph going to look like a displacement time graph? No, but it technically is. What if I had said, draw a position versus time graph for you as you travel today? Then what would it be? It would have to go back down to 0, wouldn't it? Because eventually today you're going home. Does everybody understand? But since it's only to school, it's going to look like a distance graph. But in reality, it's displacement. Everybody okay? Now, some of you walk, yes? So if you walk to school, will your lines be steep or flat? Why? Because you walk slow. You travel not very much distance in a great amount of time. What if you ride your bike? Little bit steeper. What if you drive a car? Much steeper, except what happens in the car all the time? Stops and starts. You could almost walk to school or even ride your bike to school without ever having a flat part, could you? Because you could cut across the street in the middle when there's no cars coming, right? Not wait for a light. You could do that, couldn't you? Everybody with me? All right, so I'm going to leave you with that to draw. Attempt it. I'll do my own. And then you're going to do page 155, 156, and 157. The answer on 158. Now listen to me, please, ladies and gentlemen. Please, please, please. There is a lot of practice work here. But when you look at it, it's not a lot of actual work. The reason it looks so long is because there's so many pictures. Pictures take up space, right? You have work that you can do. Now, I think there might be a screw up in the printing here. I just want to make sure. So all of you work on number 8 right now. And I'm going to check the next few pages and make sure that they're printed in the right order. Okay? You guys do number 8, and I'll be right back with you. All right. I know you're all working on your own. How do I get to school? Drive. Do I live on the highway? No, nobody lives on the highway. I live in the middle of Chilliwack. So my trip to the highway is going to be what? It's going to be weird. There's going to be stops and starts, right? And is it going to be steep or fairly flat? Fairly flat, because the speed limit is 50 an hour, yeah? I live 8 kilometers from the highway, the way I drive to work. So for the first 8 kilometers, I'm going to be pretty slow. 50 kilometers an hour is the speed limit. So it's going to take a little bit longer than 8 minutes to go 8 kilometers, right? So 10 minutes to go 8 kilometers. There's my 10 minutes. There's my 8 kilometers. And you know that it's going to be drive, flat, drive, flat, drive, flat, drive, flat, up to there, right? What happens at the highway? Way up, right? I get on the highway at exit 116. I get off at exit 92. 90. Exit 90. That's 26 kilometers. Okay? And I'm going, for ease of use, I'm going 100 kilometers an hour, and let's say it's only 25 kilometers, right? So if I go 100 kilometers an hour, how long will it take to go 25 kilometers? 15 minutes. So from 10 to 25, I'm going 100 kilometers an hour, yes? I'm on the highway, so is there a lot of speed up and slow down? On the highway? It does depend on traffic, but I'm telling you at 7 in the morning, there isn't a lot. So I'm going to go 15 minutes, and that will take me up to about 35. Right? Basically a straight line. Constant speed. What happens when I turn off the highway? It's going to look a lot like this until when? I get to school. Zig, 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 school. Everybody with me? Now, looking at that, here's the stop and go part. Here's the highway. Here's the stop and go part. When I return home, it should look pretty similar to this, right? There's a little bit more traffic, so maybe this line has a few more zigs in it. Everybody understand? Yep. All right, now listen. Page 155, all the way to 162 is these concepts repeated over and over and over and over. Please notice that in this one day, we have covered math, physics, all parts of science, because there's graphs in science all over the place, social studies, right? You guys do graphs and socials. This is important to everything, to be able to read, understand, and construct a graph. Don't blow off these pages. The reason that so much is there with which to practice is because it has so many ramifications outside of math. That is also why I'm shutting up now, because you've got 30 minutes to work here. Now, use your brains. Use your brains. Be smart about this. If you do a question, check the answers and they're all right, maybe you only do A and B of the next one. If they're all wrong, go back and talk to a neighbor or talk to me. Okay? Make sure you sketch a bunch of graphs over these pages. And make sure you explain a bunch of graphs on these pages. Because that is the best thing to do to show me you know what you're doing. All right? I am not going to say that all of that is due tomorrow, but I am going to say you should do a goodly portion of both pieces. All right? And remember, a sketch graph is fine. If you need to use extra paper, just use it. Okay? Tobby. 162. That's the end of the answers. 3 of those pages are answers. 1 second. I want to check something. Whoa, whoa, whoa! I'm the worst kind of liar. Do stop at 159. 160 is the work that goes... I thought they were printed in a weird order. 160 is the work that goes with tomorrow's lesson. Garumph. Yeah. Okay. And then we're going to have a quiz on Wednesday or Thursday. Yeah. You are blocked deep. Yep. What did I say? 157 to 60? 155 to 60? 159.